All right, so picking up where we left off last time, we were looking at ways to eliminate recursion, because as we saw with the Fibonacci, the perfect bad example here, with the Fibonacci sequence, you'll end up doing a lot of recomputations of the same thing over and over again, right? Fibonacci of 5 makes 2 calls to Fibonacci of 4, Fibonacci of 3, but Fibonacci of 3 is recomputed twice over here and over here. If you look at Fibonacci of 2, that's computed once, twice, thrice, 3 times. And then it gets even worse if you've got longer and longer calls. Like if you called Fibonacci of 65, this would be trillions and trillions and trillions of 17 trillion or so function calls. And that's not executing in any reasonable amount of time. If you go up to 100 or 1,000 or something like that, that's not executing within the heat death of our own sun, right? We're talking about billions and billions of years there. And so the solution is to use what is called memoization, right? Or one of the solutions is, where you maintain a table or a cache of results. So that when you compute that Fibonacci of 4, you don't recompute it every single time you need it. You do is you compute it the first time, right? And then you put that into your table, you cache it, so that next time you need it, you don't recompute it, you just use it, right? So for example, over here, we'll go ahead and pay for the recursion to compute Fibonacci of 4. We'll pay for the recursion to compute Fibonacci of 3. But over here, when we need Fibonacci of 3 again, we don't pay for this entire recursion over here. Instead, we've already stored the result over here, and we simply just use it. And we're going to do that in a table. All right, so I'm going to demonstrate how that's done. You're going to do that in your lab tomorrow or Thursday or something, or both, I think. Here's the program that we had last time, which is purely recursive, right? Fibonacci of negative values is not defined, so we return this flag value, -1. Otherwise, if it's 1 or 2, then we return 1. And any other value, we make the recursion. We call Fibonacci of n-1, Fibonacci of n-2, add them together and return it. I've updated it here so that we're reading n from the command line, right? And also, I'm going to do another update here so that it is a long. Now, a long is a double precision integer. It's a 64-bit integer. With 32-bit integers, we're only able to represent up to 2.147 billion and some change. Here, we can actually represent several quintillion. In fact, if we go over here to Wolfram Alpha and ask how big 2 to the 63rd, why 63rd instead of 64, one of those is the sign bit, plus or minus. -1 because the counting starts at 0, like all computer science counting. And so we can represent up to 9.2 quintillion values here. Right? And because Fibonacci grows very fast, I'm going to go ahead and change this so that it's a long, right? A long integer. When I print it out, I think that the placeholder for that is going to be LD, which is a long digit, right? And I'm going to update here this to be along here, okay? Now comes the memoization part. First of all, we need to create a table, right? My table is going to compute Fibonacci of 0, Fibonacci of 1, Fibonacci of 2, et cetera, et cetera. And so my table is going to look something like this. If I need to compute Fibonacci of n, where n is 1, right? Here's the value, right? Well, the value here is 1. N is going to be 2. Well, the value there is 2. 3 is going to be the 2 previous values here, so this is going to end up being 3, 4, 5, 6, ... all the way up to n. And so this is going to be 5, 8, 13, ... This is the one that I'm interested in, okay? Now, if I did this as a table, of course, it would actually start out at 0. Right? I'm going to go ahead and ignore that because I don't want to be off by 1. So we're going to go ahead and create a table of what size? How big is this thing then? It's not n, it is n plus 1. Right? So as a first step, let's create a table of size n plus 1, right? Before I call this function here. And it's going to be a long table because it's not an integer table, it's a table of long values. And it's going to be a pointer, and I'll just call it values. Right? I'm going to make a call to malloc like we've been doing this entire time ever since we introduced arrays. How many of them do you want? Well, it's going to be size of long instead of integer. And how many of them do you want? You said it was n plus 1. Right? We should also typecast the return value there and there. Now I've got my table, but it doesn't actually store these values yet, right? What I now need is a placeholder to indicate, has it been computed or not? Has not yet been computed. So nothing's been computing. So I need to initialize my table, right? So here's my table of values. Right? I need to now initialize my table. Now, what would be a good placeholder to say that this thing has not been computed yet? Negative values, okay. So for int I equals 0, I is less than n plus 1, because the size of the table is n plus 1, I plus plus. Values of I will be negative 1. That's going to be my flag value to indicate, just like I use this flag value up here to say undefined, I'm going to use the same flag value right here to say it's not yet been defined yet. It hasn't been computed yet. Okay. Now I'm going to take care of my base conditions, base cases. Remember that the Fibonacci of 1 is defined to be 1, and Fibonacci of 2 is defined to be 1. Right? So I've taken care of these two base conditions right here. Now it should have been 1 right here, sorry. I screwed that up. So 1, and then this was 2, and this was 3, 5, dot, 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 dot. You know it, right? All right, so I've done my base conditions here. Now I'm going to pass along this table as we go into this function. I'm going to say I want the value of n, and here's the table so far. Okay. That means that we need to update my function signature up here to take in a value n and a table of long values. All right. If it's undefined, it's undefined. We'll just simply return negative 1. The base conditions, those don't have to change either, right? If we get down to 1 or 2, then that means that it has a value of 1. This is where we need to make our changes. Here's my outline. Check to see if the value has already been computed. Right? Step 1. If so, if yes, then return it. In other words, don't pay for the recursion. It's already been computed. It's in that values table, that values array already. Right? If no, then compute it. Then A, compute it. And B, you want to make sure that you don't have to compute it ever again. So store it. Right? And then return it. Okay? There's my outline. How do I check to see if the value has already been computed? If values of n is not equal to negative 1, then that means it's already been computed. And so I simply say return values of n. I'm using the table along with n as an index to see if it's computed, and if it is, I'm directly returning that value right there. Right? There's the if yes, if no, else, right? Then I need to compute it. Well, how do I compute it? Right here, right? So long x is equal to Fibonacci of n minus 1, n minus 2, passing in those values. Right? All right. Now, before I return, I need to store it, because if I don't store it in the table, I'm not making any progress. The table doesn't get filled out. So values sub n is equal to x. And then I can return x. Okay? Now remember, it would have taken hours, days, months, years, or whatever to compute this thing. To compute, say, Fibonacci of 65, right? I forget what we did last time, but it would have taken a long time. Let's make sure that this actually compiles first of all. There we go. Oops, value, not values. Values. Oh, there we go. There's the error. All right, clear. All right, GCC. Oops. Wall, and what's wrong? Now I'm returning if else. Oh, there. Forgot my curly bracket. All right. So there we go. All right. Now let's run this. Now if I want to do some what's called regression testing here. Remember that the 10th Fibonacci number is going to be. Let's come back up over here and look at the pre-computed values that we did on Friday. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Should be 55, right? Let's find out if it's right. Hey, it's 55. What if I went one more? What was it again? 89? That works as well. What if I went one more? Now, I didn't put it up on the notes there, but the Fibonacci sequence is going to be 55 plus 89 is going to be 144. So it looks like it works to me. Let's bump this up to, say, 65. Now, 65, it's probably going to be correct. We can check on Wolfram Alpha if you really want to. But the point being here that this would have taken weeks or days or maybe even years to compute if we had used the naive solution, the recursive solution. But here, we get it instantaneously. Now, why is this? Come back over here to this diagram. Remember that we do not, come on, there we go. That if we compute this thing over here, then we end up not having to compute it over here. So when I compute the fifth one, the fourth one, the third one, when I compute this the first time, that gets stored off into a cache. So that when I come down over here and I see Fibonacci of 3, I don't have to recompute that. What ends up happening is you end up, let's go with red here. Come on. There. You end up getting rid of that entire sub-tree right there. This entire subtree is now gone. Right? If you look at this as a tree, well, we call this a tree because we've got a root up here, and then it's got a branch over there and a branch over there. And yes, it is growing down. We'll explain that in computer science too. All of our trees grow downward in computer science. Here's another branch, here's another branch. But I've taken this branch and I've basically cut off that entire branch. Likewise, when I compute Fibonacci of 2 over here, I don't need to do it over here. So this entire thing gets pruned or trimmed away. Right? So all of that's gone, all of that's gone. Likewise, all that's going to be gone, all that's going to be gone. What am I left with? I'm only left with this main part right here. No, there we go. I want it to look like that. Right there, and then fill it in. Right? So if you look at this as a tree, where you've got these branches going out, and then you start chopping off all these branches, all you're left with is the trunk of the tree. It's not good for a real tree, but it's great for computation because you don't have to compute all these branches and these leaves and all these things, right? You've cut it down to just a stick, basically. You only have to do this many computations. 1, 2, 3, 4, 5 computations instead of 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 computations, right? And it's even more stark when you look at it from, say, 65 instead of 5. That's going to be huge. In fact, that's going to be more than the number of atoms in our solar system, right? And that's not computable at all, right? Within a reasonable amount of time. So, memoization. Cache those results. You're going to do something similar to another recursive function, I think the Jacobs-Thal or something, in your lab tomorrow. And it's the same basic thing. That you check to see if the value has already been computed. If so, you use it. Otherwise, you pay for the recursion, but then you make sure that you never have to pay for it again by caching and storing the result. And you need to make sure that you're setting it up by creating an array or a table, a two-dimensional array, to store that stuff. And then you need to initialize it with values that indicate they've not been computed yet and values to indicate the base conditions there. Right? So we'll put this in the notes, make sure you've got it. Down at the bottom here. There we go. And there are lots of other ways of avoiding recursion. I wouldn't even, for Fibonacci or something simple like this, I wouldn't even bother with memoization. I would just write a loop like we did on Friday. All you need is 3 variables, A, B, and C is a temporary variable. You're keeping track of the 2 previous values, you sum them together, put that in the temporary variable, and then you move this sliding window over. Okay? All right, so questions on recursion? So let's take a look at, we'll start today on the final, let's save this, all right, there we go. We're going to start on the final module for this course, which is all about searching and sorting. And the reason that this is so important is because these 2 operations, searching through some data, sorting data, it's a huge part of computer science. It's part of data processing. They're 2 fundamental operations. You're always searching for a needle in a haystack, or you're sorting a bunch of stuff because you want to see what's the best book, or what's the worst book, or what's the newest book, or whatever, right? It forms the basis of pre-processing steps for a lot of other algorithms. A lot of other algorithms assume that this data, that input data, is sorted in some way to exploit that ordering, right? Not only that, but there are a large variety of algorithms. Sorting algorithms, you have at least 24 algorithms out there, each one with a different property, or a different approach, or a different algorithmic strategy, or whatever, right? And so you're going to find that this pops up a lot of the time. All right? These two operations pop up all the time. I'm going to show you how to do it correctly, though. All right? As a first step here, let's write a function to search a collection for a particular element. Now, before we do that, I'm going to ask you, what does that mean? What does a collection mean? What does search mean? And what does a particular element mean? Right? So what are these elements, first of all? Is it a collection of integers? Is it a collection of doubles? Yeah, go ahead. It could be a number, it could be a character, it could be a string, right? It could be anything. Right? What about that collection? Now, in this class, we've only looked at one type of collection, arrays. So that's probably what we're going to be searching through. But in other languages, you have more than just arrays. You have lists, you have sets, you have all these dynamic data structures. So what does it mean for a collection? Well, it depends on the language. It depends on what your problem is. Right? So for that reason, we use something entirely different, something called pseudocode here. Right? Here's probably a solution. In fact, I know that this is a solution or a similar solution to something that you've already written in this course. In Hack 7, I believe it was, we gave you an array of integers, and then you had to write this function called contains and contains within. Right? You were basically starting at the beginning and searching, is that it? Nope. Is that it? Nope. Is that it? Oh, that's it? Okay, go ahead and return that value, or return yes or something. Right? That's what this is doing right here. Given a collection of elements, A1 through AN, and a key element, E sub k, what we want to do is output an element A in A such that it matches the key according to some criteria. Phi if no such element exists. Right? Note here that I did not say that this was an array, right? Because that would be a C thing. Right? I did not say that these were integers, because again, that would be a language-specific thing. Right? What does equals mean? Well, if they're integers, then that means equals equals, right? What if it were strings? What would it mean? strcmp, string comparison, right? And if that returns a 0, then that means that those two things were equal. Right? What if I don't find what I'm looking for? I'm searching for 42, but the array doesn't contain 42. What would you end up returning, maybe? False? A negative value? Null? Right? It all depends on what your return type is. Those are all specific questions that we'll have to answer when we actually implement this as a function. But this is pseudocode. Pseudocode. The pseudo here stands for fake. It's not real code. This is just a basic outline for for something called linear search. I'm going to start at the first element. For each element in the collection, if that element equals my key, I'll output that element. Otherwise, if I get through the entire collection and I don't find what I'm looking for, I'll output phi, my placeholder value here, to indicate an unsuccessful search. Right? If I were to type this out in C, would it work? Would it compile? Absolutely not. If I were to type this out in Python, it would not work. If I were to type this out in Java, it would not work. It is pseudocode. It is generic, general code. Right? It is not intended for any particular programming language, but you can take this and then translate it to any particular programming language. So let's do that. Right? So let's go over here to my demo code. Right? And now I need to start answering those questions. What does it mean? Right? Well, first of all, let me give myself a collection that I can start searching here. Right? I'll call it array. Right? And let me I'll give it some values here. I hate doing values like that, so random.org. Right? Numbers. There it is. I just want numbers. Integer generator. There we go. I don't want that many. I just want 10. One column. 1 to 100. That's good. Give me my numbers. Come on. Fine. And then adapt them over here. There. All right. So, comma, 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 comma. Say what? Do a what? A chameleon? A comma chameleon. Okay. Yeah, culture club. All right, there we go. There. All right, and how many was that? I think it was 10, right? So I'll keep track of that here as well. All right, or n is equal to 10. There are 10 elements there, right? All right. So what's my key element here going to be? Let's say that I want to search for, I don't know, 7. Is it going to be successful? Yeah, because you see it's right there. But you as humans looked at that and immediately saw the 7, right? But in your mind, what we were actually doing was you were looking at the first one, that's not it. You were looking at the second one, that's not it. You were looking at the third one, that's not it. Until you finally got over here to the 7 and said, yes, that's it, right? So let's design a linear search function, right? I don't know what my return type here is going to be yet, but I'm going to call it linear search. We'll understand why it's linear after we've analyzed it, okay? So what are my inputs to this thing? The array, okay. Am I going to be making any changes to the array? So const int star array, right? Because I'm not going to be making any changes. What else do you need? The n, the size of the array. And finally, what else do you need? As in, like, the key that you're searching for? Right? I'm searching for this needle, and here's my haystack. Here's my needle, right? I want to know if 7 is going to be in this array. Okay? All right. Okay. For int I equals 0, I is less than n, I plus plus. For each element in the array, if the array element I is equal to my key, then I'll return something. Now I've got to answer that question of what my return type is. Otherwise, if it's unsuccessful, I return something else. Okay? That is basically this. Right? For each element in the collection, that was a basic for loop. For int I equals 0, I is less than n, I plus plus. If the ith element in the array is equal to my key element, then I'll output or I'll return some value there. Right? My collection ended up being an array, right, of elements. And because it's 0 indexed, it'd be 0 up to n minus 1. And a key element here is going to be an integer, int key. Right? So I'm taking this pseudocode and I'm translating it to actual code here. Okay? Now, what should our return type be here? What information do you want to know? If it's a simple yes or no question, Boolean. Yes, I found what you were looking for. Contains within. Right? What would be even more useful, though? Int. I could return the value. So let's document that. Right? Searches the given array ARR for the given key element, and returns the key element, key value, if found. Right? Oh, okay. Well, wait a second. I gave you the array and I gave you the key. Why would I need the key back? Right? I gave it to you as input. Right? Yeah. The position for the given key element and returns the index at which it finds it. Right? In this case, what would it end up returning? 0, 1, 2, 3, 4, 5, 6? Yes, it contains it, and it's at index 6. Right? So it returns the index at which it finds it. All right, fine. Then, what do I return right here? I, because you found it at the ith index. What do I return here then? -1. I didn't find it, so what's an index value that is unmistakable as invalid? Any negative value. -1 is good. Document that, right? Returns -1 if no such element is found. There can be unsuccessful searches. Maybe that haystack doesn't have any needles in it. All right, let's see if it works. Linear search. I will pass in int index would be linear search of array n and key, right? And I'll check to make sure that it's in there. If the index is greater than or equal to 0, then it was successful. Printf success. All right, found at index %d and the line of index. Right? Else, if it's negative, that means that it was unsuccessful. Printf failure, right? %d not found, and the line, and I'll say that the key was not found. Right? Let's go ahead and make sure that this compiles and works. Right? Success. I found it at index 6. Right? Let's make sure that it works with other values here. Say 75. Why did I choose 75, by the way? That's the last one. That's an extremal value. Right? Yay, it found it at index 9. What other extremal value should I probably check? 54. Right? And you'll find it at index 0, success. What's another thing that I should probably test? Failure. 42. 42 not found. Okay. Great. Okay. There's my first linear search algorithm. As an alternative, another thing that you could have done is you could have returned a pointer to where you found it. Oh, I found it. It's at that memory address over there, right? Literally pointing to it. Then I would have returned what? Ampersand a sub I, right? The memory address of the element. Oh, ARR sub I, sure. Right. What would I have returned in this case of an unsuccessful search, though? Null. Right. That's the only thing you can return when you're returning a memory address. But I'm going to keep it simple. Let's go ahead and return it to all that stuff. Right. We'll go ahead and go with this. Right. But there are alternatives. Okay. All right. What if I did this on a huge array? What if I did this on 1,000,000 elements? Right? Let's think about this in terms of best case, worst case, and average case. So what's the best case here? Right. Well, first of all, we need to quantify. What are we doing? What work are we doing? So let's come over here. What work is this function actually doing? Well, I've got a for loop here. So if you want to analyze this, there's an assignment. There's a comparison. Plus plus, that's going to be an addition, right? So there's a bunch of work going on here. There's another comparison. There's a return value, right? What do you think is the most important thing here, though? I'd say that it's this comparison right here, right? Because you're doing that every single time. Is that it? Is that it? Is that it? Until you get down to what you found. In which case, it doesn't matter what this for loop is doing. That an addition, another comparison, or whatever. Right? If I find it at the first element, I'm done. Right? I only had to do one comparison. So our work, right, or resource, or time, the time that it takes to do this is quantified by the comparison of key elements, right? That whatever line it was. If you want to highlight it over here, let me go ahead and get rid of all that annotation. There we go. And where is it in the pseudocode here? It's this thing right here, right? It's that comparison. Okay. So now let's think about this in best case, worst case, average case scenario. Best case. You get lucky. And you find it where? Yep, you find at index 0. In which case, how many comparisons did you make? Number of comparisons, or comps for short, would end up being 1. Just 1. Right? You got lucky and you only had to do one thing and now you're done. Right? What about in the worst case? Right. If there are 1,000,000 elements in there, it's going to be 1,000,000. If there are 10 elements in there, it's going to be 10. Why, though? Look through every single one. Look or compare every element, right? In which case you find it at the last, right? So find at index what? N minus 1, or not found. Failure, right? Because that's going to be the same thing. You get down all, that's not it, that's not it, that's not it, dot, 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 that's not it, right? And you end up comparing it with all n of them. If n is 10, you made 10 comparisons. If n is 1,000,000, you made 1,000,000 comparisons. If n has 50 billion elements in your array, then you made 50 billion comparisons. Okay? What's the average, though? Average. Now, a full analysis on this is going to require a probability distribution on a successful search, and then you sum it all up, and you maximize it, et cetera, et cetera. I want a naive way of looking at it. 500,000. What? 500,000. 500,000. Why though? In general, let's keep it just with respect to n elements, right? So the worst case is you make n elements. You make n comparisons. The best case is you make one comparison. What's the average of those? 2, right? Or let's just go ahead and say that it's about n divided by 2, because this 1/2 right here, I want to ignore that, all right? So n divided by 2. If n is equal to 10, then you end up making, on best, you make one comparison. Worst, you make n comparisons. And in the average, you make n divided by 2 comparisons. Or, sorry. This is one comparison, 10 comparisons, you're right, 10. And then this would be 5 comparisons. Okay? What if n was 1,000,000? Then the best is going to be 1. The worst is going to be 1,000,000. And the average? 500,000. There we go. What if it's 1,000,000,000? Then the best is going to be 1. 500 million is, on average, and then 1 billion in the worst case. Right? The best always 1? Yeah, the best is always 1, right? So, should we consider that? If you go to a casino, are you always going to assume that you win? Right? No. In fact, you should always assume that you lose, because you eventually will. Right? Right? So we're not going to assume the best anymore. Right? What about the average versus the worst? In other words, in general, if it's n versus n divided by 2, right? Tell me about those functions. What if I were to graph them? Here's x and here's y, or n, and then number of comparisons. All right. What does n look like? The graph of n.
Yeah, like that.
Like this. I'll let it straighten out. There we go. N. What does n divided by 2 look like? But half. In other words, there's a coefficient out there, and so the slope is 1/2 sitting out front. Right? But now, and it's not exact because, of course, I'm not intersecting with the xy axis over here, the origin, right? But there's what it looks like about. Is there any difference between these two functions as far as mathematics is concerned? Like this 1/2 sitting out front here, does that really matter as n tends towards infinity, as you get larger and larger arrays? It does in some sense, right? But what kind of function is this? It's not a quadratic function. N squared would be quadratic. This is what?
Linear.
It's a linear function. Right. What about this function right here? Is that a quadratic? No. It's also a linear function. Right? They're both linear functions. So from the perspective of mathematics, they're not that much different. Right? In fact, there's another coefficient sitting out front here, C and C, that quantifies how fast your computer is. That one comparison, how fast can you get it done? Well, on this computer, I can get it done in one microsecond. On a computer twice as fast, I can get that done in half a microsecond. On a computer that is 10 times as fast, I can get that done in a nanosecond or something like that. Right? At the end of the day, there's this constant sitting out front here that we don't know what it is unless it's on a particular piece of hardware. So do we really care about that constant? No. We care about the algorithm itself. Right? So I'll take this constant and fold it into this constant over here, and we just have constants sitting out front. Right? Both are going to be linear. Both are linear. That's why we get linear search. Right? Now think about the implications of that. If I start out with n elements, and it takes me t time to compute, say that I double the number of elements. I go from n to 2n. What would you expect the time? Would you expect more time or less time or the same amount of time? Right? Think of it like this. I had 1 million elements in my array, and I went up to 2 million elements in my array. Right? What would you do to the, and what would end up happening to the time to compute this linear search? Double. 2t. Right? What if I went up from n to 10n? What would you expect it then? 10t. Right? The growth rate is linear with respect to the input size. There's another way of thinking about this, but it requires calculus. Right? So if you're not in calculus, it's not a prereq or it's not a co-req. So you can feel free to tune out for a second. But how can I quantify the growth rate of a function in calculus? The slope, which what operation will give me the slope? The first derivative. What's the first derivative of n? 1. What's the first derivative of 1/2 n? 1/2. So what is the growth rate of both of these functions? Constant. Right? It doesn't really matter. One constant is 1, the other constant is 1/2. It doesn't matter. You'll end up replacing that with some c at the end of the day that quantifies how fast your computer is. Okay? So the growth rate is constant. If I go up an order of magnitude by 2, then that means I can expect double the time. If I go up by an order of magnitude by 10, that means it's going to take me 10 times as long, or it's going to be 10 times as slow, right? So that's why it's called linear, okay? So the question is, can we do better? Let's see. Insert from... where's my stuff? I need a sorted array. All right, this one's good enough. All right. It's highlighted there, but that's all right. You'll understand what the highlight is there for in a second here. All right. Suppose that I'm searching for 42. Okay. How much time do we have? Yeah, we're good on time. Let's just explain this for now. Now, it's sorted. Do I have to start at the beginning? Well, that's not it. That's not it. That's not it. That's not it. What if instead I started in the middle with this highlighted value right here, 12? Okay. Now, what can you immediately rule out? Is 42 going to be anywhere over here on the left-hand side? No, because it's sorted. And everything over here is going to be less than 12. Right? If 42 exists in this array, then it's going to be over here. Essentially what I've done is I've cut the array in half. Right? I went from n down to about n divided by 2. Right? I've divided it in half. I've divided it. Now let's conquer it. Right? Let's do the same thing again. Right? And I don't have the color. I can match that. Green. There we go. Look at this one right here. Right? Now 42. Is it going to, that's not it, right? So that's not equal to 42. So I need to look at either the left or the right. Should I even bother going to the right if I'm looking for 42? Nope, because everything over here is greater than 102 because it's sorted. So I can immediately rule out this part over here. I've cut it in half again. N divided by 2, n divided by 2. What is that? N divided by 4. Right? Okay. We'll come back to that when we actually analyze this thing. All right, so now I've cut it down to just this part. Everything over here has been cut out. Now I'm down to 2 elements. What is the middle here, technically? It depends on how you define the middle, but I'll go ahead and define it like that. All right? And I'll say, oh, okay, Successful search. It's at index 7. Right? How many comparisons did I need to make to do that? 1, 2, 3. 3 comparisons, comps. Right. Now, how many comparisons would I have had to make if I used a linear search on this? 8? Why 8? 1, 2, 3, 4, 5, 6, 7, 8. Oh, okay, I found it. 3 versus 8. Which one do you want to do? 3, right? So now we have to decide. Now we have to actually program this, though. Right? It's going to be a divide and conquer strategy. Here's my binary search. This is called binary search. Here, my input is going to be a sorted array or collection or whatever, right? And a key element, k. Right? And I'm going to keep track of indices, index left and index right. The idea here is that I'm going to keep track of these indices, right? And let's go ahead and get rid of all that. Right? Initially, the left is going to point here, and the right is going to point here. Right? Because I want to search the entire array. It's going to be 0 and 10 initially. Now, how do I compute this middle index right here? Take the... So, left... here. The biggest... What do you mean by biggest?
Biggest index.
So that's always going to be... The right is always going to be the right, and the left is always going to be the left. So it's going to be right. Okay. Then what? Plus left. How do we get the guy in the middle? Divide by 2. Right? That gives me M, this middle index right here, or mid or middle or median or whatever you want to think of it, right? Because if it's sorted, it is the median and the first iteration here. So I'm going to keep track of this left index and this right index, compute the middle index, okay? So that's my first step here. M is going to be left plus right divided by 2. Right plus left divided by 2, it doesn't matter. If you've got two numbers on a number line, right, how do you get the number right in the middle? You take the average. Okay? Now, if the array of M is equal to the key that I'm looking for, I'm done, right? Success. S-U-C-C-E-S-S. Success. Output M, the index at which I found it. Okay? And by the way, why is pseudocode written like this? Right? We don't have opening and closing curly brackets. We have these things right here because it completely discourages you from writing actual code, right? There is no way that you can actually write this in any meaningful way in any code editor, right? This vertical line, right? You can get code editors to display it like that, but in fact, I can show you, right? You can do this in your in VS Code, can't you? You can't do it in VS Code? I thought you could. There should be a way to do this. You can collapse things.
It's in the settings, yeah, 'cause I've seen it collapse.
Yeah, I don't know how it's set up, but anyway.
Mess around with the settings.
Okay. There is a way to do it, I'm sure, right? All right, so that's not the thing that we're looking for, right? That's not it. So I need to decide, do I search left or do I search right? Right? How do I decide that? Let's go ahead and get rid of this, right? The thing I'm searching for, key, is less than the array element at index M. That means search where? Left. Right? Otherwise, if the key element is, and here I'll switch them around. If a sub M is less than the key element, that means search right. Okay? All right, I don't like, come on. Copy. Oh, they've changed everything. Which one would be copy? That one? Paste? Okay, there we go. All right. And you know what? Move this up a little bit. Move all that up a little bit. Oh, come on. There we go. Now it's all aligned, right? I'll give you a much cleaner version later on. Okay. So, if I search left, how do I go about doing that? If I want to search left, here's left and here's right. Right. I want to search now in this part here. Do I update my left index? No. I update my right index to middle, except that we already looked at middle and we decided that that wasn't it. Middle minus 1. All right. So I'll say the right index is equal to m minus 1. Right. Likewise, what if I want to search right? I need to go over here now. I update my left to be m plus 1. Right, or left is equal to m plus 1. And then I repeat. Until when? Repeat until ... Until I find what I'm looking for. All right. But what if what I'm looking for doesn't exist? I'm looking for 37. Right. I end up in this section. I end up cutting this out, and that's not it either. So return -1, but what condition? Right? Until what? Think about this, left and right. Left, right, left, right, left, right. And then if they're equal, I still want to make sure that that 1 is not the thing that I'm looking for. What happens, though, when they pass each other? Yep. Repeat until left has exceeded the right. They've gone past each other. Right? And then in which case, output phi or -1 or null or whatever you're going to do. Okay? We don't have enough time to program it, but we will next time. Right? As a preview of this, the complexity on this, the number of comparisons, is going to end up being log n. Right? Versus linear search, which is n. What is the difference between these two? This is obviously faster, smaller, and therefore faster. But how do you get log n out of n? How would I go the other way? I'd have to exponentiate it, right? By the way, we're self-respecting computer scientists, so all of our logs are base 2 because everything's binary, right? It's not base 10. It's not base e like those math folks, right? Instead, it is base 2. I would have to raise 2 to the log n to get back 2, or to get back n, excuse me. In other words, this is exponentially faster than this is over here. Right? That's going to be a huge speed up, and we'll analyze that next time after we've written it out. Okay. All right. See you on Wednesday.